In this next part of the problem, we still have the spherical charge here that has a radius of r and a total charge of q, and our goal is to find out what the amount of energy it takes to create this spherical charge here. And specifically, we were told to use a certain equation in order to find this out, and that equation is written here. And of note for this equation, let me rewrite that. Of note for this equation, this is for all. This was made to be used for over all space. So this is the work over all space. So if you have multiple of these and that share the same space, it doesn't really work out. So since we're only looking at one isolated charge here, this actually does end up working out. So the next piece is to figure out what the E here is, and that's the electric field, not to be confused with energy, because that seat's basically already taken for electrodynamics, so we just refer to it specifically of what type of energy it is, and that's work in our case. And so we'll go ahead and expand this out to expand the two areas in which there's an electric field here. There's an electric field here that's on the inside, and there's an electric field on the outside as well. And those are two different values that we found out previously in different problems, but we'll go ahead and make it explicit here. So we'll say this is that's the electric field for the inside, and then we superimpose that for the electric field on the outside. There we go. And now we'll go ahead and just write it out specifically. So if we do a Gaussian surface right here, that's a little bit not quite in the middle, but if we do that Gaussian surface in the middle, the E on the inside here, and we found this out from a previous problem. I forgot specifically what it is, but at this point we should be able to readily be able to find these out using Gauss's law. And then if we also do like a Gaussian surface on the outside of this thing, let's make it a different color so it's not confusing. A Gaussian surface on the outside, we'd find that that electric field here on the outside is equal to, it just basically looks like a point charge. You can essentially collapse this down to a point charge. All right. So we can just go ahead and just take these two values and then throw them into our values. Not specifically like that, actually, it would be crossed like that. But all right, let's go ahead and throw them in here. And then we'll go ahead and expand them out. So I'll pull all the constants out of the integral sign. And then since this is a d tau, so a spherical volumetric charge, I'll go ahead and just write those out explicitly here. So for the electric field on the inside, see here we have, and again, everything is squared here. So I'm just going to go ahead and square all the values, all the constant values, and we're integrating over all space. So I'll go d theta on the outside, d phi, and then r. And so it's r squared, and then times the volumetric charge, which is r squared sine, or sort of the differential volume. Running out of room, so I'll just go ahead and make an indent right here and just do a plus sign. Pull all the constants out of the integral sign for the electric field for the outside. Now this gets a little bit different actually here, so we're going to want to pay attention to this portion. So as we integrate out, it goes from 0 all the way to r, 0 all the way to r here, big R, and then this next part of the integral goes from big R to infinity. So since we're dealing with the E on the outside right here, now we're shifting over from R out to infinity right here, since we covered the inside of the electric field to here, and we're just going to make it continuous all the way from 0 to infinity with R as the that threshold where things get a little different. And so you know what, actually on this one I forgot the R. I'm sorry. Let me go ahead and move that over. You guys are probably noticing already in the screen right now. Oops. I think we can get through before the battery dies. All right, let's see here. Now we have an r to the fourth, right? And then we have our volumetric charge, or our differential volume. d phi d theta, and parentheses. We'll go ahead and start cleaning up some stuff right now. So both of these have an epsilon naught constant, so we can go ahead and start canceling out that one of those epsilon naughts. And then over here, we do have the r squareds that we can cancel out and turn this into a 2. Let's go ahead and rewrite everything, pulling out all the constants that are common to both of the terms. Let's see here, 16 times 2 is 32. We have a pi squared, epsilon naught. So those are common to everything. So these only have r in the variables within the integrals, so that we can go ahead and evaluate the integral signs, the integral limits for phi and theta, and that equals to 4 pi for both of them. So I'll go ahead and put 4 pi on the outside here. And then, let's see here, 4 pi for both of them. And then let's move this up a little bit. 4 pi for both of them. And then we have a 1 over r to the 6th still as a constant for this one. 0 to r right here. R to the 4th dr plus, there's no constants in front of this one. R to infinity, 1 over r squared dr, right? Now we can go ahead and evaluate that integral. And you know what? Let's just do some cleaning up right now. We can get rid of this 4 and turn this 32 into an 8. This pi squared can just go into a pi in the denominator. We'll go ahead and rewrite all these constants out in front. 8 pi epsilon naught. And then we'll move into the integrals here. So whenever this is a relatively easy integral, so that's just r to the 5th raised to the 5th plus, and this is a double term for the integral, so actually, let me do a little bracket. That ends up being a negative 1 over the top limit, which is infinity, 1 over infinity. And then we also have a plus, so it's minus and negative 1 over r for that limit. And of course, we have a negative 1 over infinity, so that ends up going to 0. And this ends up being a plus sign right here. So I'll just go ahead and make that a plus sign. And if we go ahead and look at that, let's see here. We will just go ahead and drop down our constants here. We'll clean things up a bit over here. So this is 1 over r, because we can just go ahead and cancel those out right there. That's 1 over r times 1 to the 5th plus 1 over r. And already we're getting really close to the answer. And let's see here. So we can go ahead and pull out that 1 over r. That's in the parentheses. So q squared, 8 pi epsilon naught, 1 over r. Everything on the inside, that's 6 over 5. And then finally, that all equals to 3 over 20. Once we do some of the math here, because that ends up being a 3, that cancels out to a 4. So 4 times 5 equals 20. Let's see here, q squared over pi epsilon naught times r, which is exactly what we got in our previous part of the question right here. So that is the work that it takes to create this spherical charge here with spherical charge distribution with a total charge of q, radius of r, using this specific one. I think in the next part of the problem we'll do a different method than this to figure that out, just to show that they're all consistent.